Good afternoon. Well, I thank Technobiz for this opportunity to present some of my methods I developed to measure solubilities, nucleation rates, so primary and secondary nucleation rates, and I think this is a nice opportunity to show them to you. So I'm based at the University of Strathclyde in Glasgow. So rather than showing a picture of Glasgow, maybe it's better to show a picture of Loch Lomond, very close to Glasgow, just to show you that Scotland can be sunny. So I'm within the CMEC, so the Future Manufacturing Research Hub, that the research is continuous manufacturing and crystallization. So that's also part of the Strathclyde Institute of Pharmacy and Biomedical Sciences. My group is part of that. And I'm located in the Technology and Innovation Center of the University of Strathclyde. So my research group is investigating industrial crystallization. So I made a list of the PhD students and postdocs in my group and their topics. So I roughly divided them into 4. So continuous crystallization, crystallization kinetics, protein crystallization, and chiral resolution. So it's all about crystals and their product quality. And if you look at this, this picture, you can see what we can define as product quality. It's the size and the shape of the crystals, which is also related to the crystal structure. But also purity is a very important part of the crystalline product. It's often forgotten because crystallization is a very efficient separation technology, which usually just in one step arrives at the product quality, product purity of 99.9%. So crystallization is a highly efficient separation technology, and it has the added advantage that it results in a particulate product. So how can we control this product? That is by controlling crystallization, of course. So crystallization is a process with several sub-processes connected to it. So we first have to create particles by primary nucleation or secondary nucleation, and these particles then can grow out by crystal growth, and sometimes you have agglomeration occurring. So these sub-processes of crystallization are influenced by many parameters, such as supersaturation and solution composition, and also the hydrodynamics that take place during the process. One thing we did within CMEC is to develop a crystallization design workflow for cooling crystallization. So these are the steps one could follow to make a good crystallization process design. So I will be talking about the solvent, the solubility determination, which come back in stage 2 and 3 of the crystallization design workflow, where we screen for solvents and we select the solvent for the process. But I'll also talk about primary nucleation and secondary nucleation, which come back in stage 5, which should lead to an increased system understanding. So the first thing to do is to know the solubility to come to a good crystallization process design. So how to measure solubility? So let's focus on crystallization from solution, and then we have a number of crystallization methods. For instance, evaporative crystallization. And often you would choose evaporative crystallization, where you evaporate the solvent to increase the concentration. When you have a relatively low dependence of the solubility with temperature. So yeah, you see in the figure concentration against temperature, and the blue line indicates the solubility, and the solubility is hardly influenced by temperature. So that is a good parameter to choose evaporative crystallization. Then cooling crystallization makes use of the large solubility dependence, temperature dependence of the solubility. So like shown in this in the second graph. So you need a large change in solubility as a function of temperature, and you would prefer a low solubility at the low temperature at the end of your cooling crystallization, so that you can remove most of your solute from your solution by cooling crystallization. So a third crystallization process is anti-solvent crystallization, where you would use the decrease of the solubility as a function of the anti-solvent you add. So the decrease should be highly nonlinear, because at the same time that you decrease the solubility with the adding anti-solvent, you would also dilute the system. So your decrease in solubility should be larger than your decrease of the concentration due to the dilution. And then the fourth crystallization method is precipitation, which can be seen as a combination of a reaction and a crystallization. So you react to a very insoluble product, which then precipitates out. And there you see that the solubility at a particular temperature is a function of both reagents that combine into the slightly soluble product. So crystallization from solution and the method you would choose strongly depends on the solubility of the compound. So another thing you use solubility for is the yield. So the yield is related to the concentration and the solubility. So the concentration exceeds the solubility, and the difference is the amount that you can crystallize out in your crystallization process. So that's indicated by the green line here. So the yield in this particular example is 80 milligrams of crystals per milliliter of solvent. And that means that if you wait long enough, you would crystallize 80% of your solute. And 20% of the solute remains in solution. So it's important to know your solubility, so that you also know, say, the maximum theoretical yield and the loss of material, because some solute will stay behind in your solution, the remaining solution. So how do we measure solubility? So we have to define solubility then, and we can define solubility as the equilibrium between the crystalline solid in the suspension and the solution concentration of that suspension. So if we make a suspension and we wait long enough, then there will be an equilibrium, and the solution concentration at that equilibrium would be the solubility. Well, it might take a long time, but that is the right definition for solubility. So here we have a suspension, and we have a very pure crystalline phase, and the surrounding solution has the concentration which is equal to the solubility. So one quick way of measuring the solubility is just by detecting crystals in a suspension. If there are crystals present, you might have equilibrium, and then we can increase the temperature very slowly so that the crystals dissolve, and then at some point you will see that the crystals disappear, and then your concentration would be exactly equal to your solubility. So the temperature at which that happens is the clear point temperature, and that is equal to the saturation temperature of the solution. So we can do a lot of measurements in this way, and there's commercial equipment available to do that in quite a standard way already. And you can also obtain say kinetics of the process by cooling down and crystallizing out. You can determine the kinetics of the crystallization process. So a typical outcome for clear points is shown in this slide. So here's the temperature against time, and then the orange line indicates the temperature profile. So we cool down, wait a little bit, and then heat up, and cool down again, and then heat up again. So if we start with a clear solution at the left, say the transmission, which is the green line, would be close to 100%. That is the other y-axis on the right. So it would be close to, it would be 100% because it's a clear solution. And we cool down, and then at some point we get crystals in the sample. And these crystals are detected because the transmission of light goes down. And you really see that happening in a very short time, that the transmission goes from 100% to 0%. And then we have a suspension which we can gradually heat up and see where the crystals disappear to determine our clear point. So the clear point is indicated by the red indicator. So it's around 600 minutes. We see that the transmission of light becomes 100%, and the corresponding temperature in the temperature profile is then your clear point temperature. And we can do that so twice in a row for the same sample, and we can determine then clear point temperatures, and you see that they are quite close together. They are quite close to each other. Usually we use here a heating rate of around 0.3 degrees per minute to get accurate clear point temperature measurements. We tested sometimes, say, what is the effect of this heating rate. So this graph is showing the clear point temperature as a function of the heating rate for the same sample. And you see that if you increase the heating rate too much, then the crystals cannot keep up with the dissolution. So they would only dissolve at a higher temperature, which is then not the clear point, the actual saturation temperature. So the actual saturation temperature would be the one where your heating rate would approach 0. But we have to make a balance between the fastness of the measurement and the accuracy of the solubility we want. So in our case, we often use 0.3 degrees per minute as a good heating rate. So we can determine the saturation temperature if, say, the crystal detection limit is low enough. So crystals should be detected by this transmission of light, of course. And there is let's say, some sort of detection limit. And if it's low enough, then we can assume that the clear point we measure is the same as the saturation temperature. So we need fast dissolving crystals. If they are not dissolving fast enough, we have to measure at lower heating rates. And it's also good to check during these measurements that you don't have fouling, or say fouling is crystals connecting, crystallizing on the walls, or crowning, which is that you get say a crown of crystals just above the liquid level. So it's always good to check during the measurement that these things do not occur. So check the vials during the measurement. So if you get reliable data, you get data which you can plot nicely in solubility graphs. Say, for instance, the mole fraction against the clear point temperature, which is shown here for isonicotinamide in ethanol. But we can also do more complex measurements in more complex multi-component systems. I just want to give one example where we screened the co-crystal system. So we have 3 components in there: the solvent, pharmaceutical, and a conformer. And by picking typical concentrations of the samples, we can screen the phase diagram and show whether a co-crystal exists or not. So, once we know the solubility, we also know the supersaturation in a clear solution if we know the temperature. So then we have a good value for, say, an accurate value for the supersaturation ratio. And we need accurate values if we want to accurately measure primary and secondary nucleation rates. So first, primary nucleation rates. So our idea was to develop a method for measuring primary nucleation rates based on the measuring the transmission of light of these samples. So we know that the clear point now, so upon heating there's a temperature that the suspension turns into a clear solution. But we also have cloud points where upon cooling of a solution there is a temperature that crystals will be detected. And then the difference between clear and cloud points of the same sample is the metastable zone width. So if we look at the measurement here, so this is showing the temperature and the transmission of light. So the temperature in red, that's the temperature profile, and in blue is the transmission of light. So we start with a suspension, so the transmission of light is 0, and upon increasing the temperature, we dissolve the crystals until there's a point that all crystals have gone, so around 7.5 hours within the measurement. And this clear point temperature is about 36 degrees. So then we have a clear solution which we can cool down again, and then around 11 hours within the measurement we measure a cloud point, and the cloud point temperature is in this case around 22 degrees. So the difference between the two is the metastable zone width. So that is the zone in which no nucleation occurs with the used cooling rate. So that would be a good thing to know if you do a seeded cooling crystallization, for instance. So within the metastable zone width, we can also do nucleation rate measurements, because within the metastable zone width, we have a supersaturated solution. So given enough time, you might see the appearance of crystals due to primary nucleation. So then we chose to measure induction times. So those are measurements of clear solutions at a constant temperature, where we just wait until we see crystals. So a typical measurement is shown in the graph, where we have a clear solution at around 9 hours. And then we crash cool to 25 degrees. So that is just before 10 hours we arrive at that temperature. And then we stay at 25 degrees to record the time it takes until we see crystals. And this time is indicated by the decrease of the transmission of light. And this happens roughly, say, close to 11 hours within the measurement. So we have roughly in the induction time of 1 hour. So we use 1 milliliter stirred solutions for this. So that's in the crystal 16, where we create this constant supersaturation, and we measure the induction time, and we do this a large number of times under exactly the same conditions. So that would result in a graph like this, where I plotted the induction time as a function of the experiment number. So under exactly the same conditions, we get a large variation of induction time. So they vary from roughly 1,000 seconds to 10,000 seconds. So they are the same conditions, but say the stochastic behavior of nucleation is responsible for this variation. So the variation itself contains information on the nucleation rate. So one thing we can tell already, because this variation is very large, that the crystal nucleation rate is very low. And we also observed this in some experiments in the crystalline. So we see that if we are lucky enough in the stirred solutions at a constant temperature where we have supersaturation, if we are lucky enough, then we see a large parent crystal floating by the camera before we really detect any induction times with this sample. So the process is that you first form, you supersaturate the solution, then you form a parent crystal with by primary nucleation, and this grows out to large sizes and then probably hits the stirrer, and many fragments are created which are responsible for the detection of crystals by the decrease of the transmission of light. So it's a two-step process where we nucleate, and then we need growth and secondary nucleation to detect the crystals. So there's some lack in our measurement of induction time. It's not the point of the induction time is not the point of nucleation, but it is the point where we detect a large number of crystals due to the nucleation of a single crystal. So we observe this in many stirred solutions. So we really think that this is something that is a general mechanism. So this single nucleus mechanism. So let's go back to this plot of a lot of different induction times for the same process conditions in these 1 milliliter stirred solutions. So nucleation is a stochastic effect, a process. So we should be able to analyze this data and obtain a nucleation rate. So then we should make it a bit nicer graph by determining the induction time probability. So that's on the right, where we plotted the the probability that you observe that you have observed crystals in a sample at a certain time. And we can determine that from our experimental data. So the probability is at a certain time is just the number of samples in which we have observed crystals divided by the total number of samples. So you see that this probability increases from 0 to 1 with time. And we created a model to describe this, which is shown in this equation. And this equation is a function of the nucleation rate, the J, and the growth time, Tg, which tells something about the lag we have in the detecting nucleation. So we detect the presence of crystals rather than nucleation. So we need growth and secondary nucleation to take place to detect the crystals. And that is incorporated in this Tg value. So we can fit this equation to the data in the right graph. And then we get a nucleation rate of 630 per cubic meter per second and a growth time of almost 1200 seconds. So this allows us to determine nucleation rates under many conditions for many different compounds and investigate nucleation, primary nucleation rates and try to understand the primary nucleation rate process. So here's a lot of data for different systems, and they all behave in a similar say, way, these induction time distributions. So the larger the supersaturation, the faster the probability rises to 1. And we can measure many systems. We can also measure the nucleation of proteins, and we can, with and without templates, and we can measure the nucleation rate of meta-organic frameworks even. To give one example, here is the probability distributions of dipropylene in IPA and DMF, 2 solvents, and the probabilities in the graphs are given in the same with the same axis for comparison, and the green points are points done under the same supersaturation. So you see that in IPA the probability rises to 1 much faster than in DMF. So that means that the nucleation rate at the same supersaturation is much higher in IPA than in DMF. So we can analyze that, so we can fit all the data to the equation to obtain the nucleation rates, and we can analyze these nucleation rates even further with classical nucleation theory, and that determines say from the nucleation rate equation the A and the B values. So the A is responsible for the kinetics of the nucleation process, and the B determines the energy barrier for nucleation. So if we analyze the nucleation rates, we find that the A value is, say the P exponential factor is not really different for both systems, but the B value determining the energy barrier is. So it shows that dipropylene in DMF is much more difficult to nucleate, so it has a higher energy barrier than dipropylene in IPA. It also shows that our pre-exponential factor is much smaller than we expect from theories, which indicates that there is some kind of heterogeneous nucleation process taking place. So there are some kinds of particles in the solution which cause heterogeneous nucleation. So we investigated that a little bit more by investigating induction time distributions in untreated samples and filtered solutions. And you see that in the filtered solutions, the induction time probabilities are on average much lower, which means that the filtration removed certain particles from the solution, so that the heterogeneous nucleation rate is decreased. So maybe not all particles are removed, but only a fraction of them. So there's still nucleation, but nucleation rate is decreased. So it tells us something about the nucleation rate mechanism. We have heterogeneous nucleation. And just because it is, say, the middle of the lecture, and it is nice to show, I would like to show that that you can increase the nucleation rate of bubbles in Mentos in Diet Coke. You can increase the nucleation rate by adding Mentos in Diet Coke. And as you see, it can have a very large impact. Good, so this was primary heterogeneous nucleation rate we measured. And we also thought of how to measure secondary nucleation rates in these solutions. So we want to develop a secondary nucleation rate measurement method. And secondary nucleation can be due to already present particle hitting the stirrer, or due to the flow around this already present particle removing small particles from this surface. So we want to determine secondary nucleation rates. So the first step we did was to measure the metastable zone of isonicotinamide in ethanol. So the black line is the solubility of isonicotinamide in ethanol, and then the metastable zone, the metastable zone limit is the red line. So in between the red line and the black line, you do have supersaturated solutions, but with the cooling rate we use, we don't see any crystals within that region. So that is also shown here, where the temperature is plotted against time. So the red line is say we constantly cool down, and we have a saturated solution at 25 degrees. So if we cool that solution down to 16 degrees, 17, 16 degrees, we will detect crystals. But we can also just stop cooling at 20 degrees and then wait until we see crystals. So we did that for 16 samples, and the dots, the green dots at 20 degrees show the induction times we measured in these 16 samples. And we can do that for different temperatures and the same solution, which is saturated at 25 degrees. And we obtain this graph, so which shows, say, the region in which we don't detect any crystals at a particular temperature. So, for instance, for 21 degrees, we have a region of, say, about 15 minutes where we don't observe any crystals due to primary nucleation. So this allows us to investigate secondary nucleation in these supersaturated solutions at 21 degrees. So we can, for instance, add a single crystal to these such a supersaturated solution and then records the suspension density in time. And this suspension density tells how many crystals are present, so it tells also the secondary nucleation rate. So the process is we have a solution which is saturated at 25 degrees. We have a clear solution. We cool down to a certain low temperature to create a supersaturation, and we know when primary nucleation would occur. So we have roughly 15 minutes to 14 minutes to investigate secondary nucleation. So we can, at some point, we can add a single crystal seed to these solutions. So if we do that, we have to, in order to relate, say what happens, what we measure in the file to secondary nucleation rate, we have to make a calibration of the suspension density. And that is what we did with monodisperse polymer particles. So we use different suspension densities of these monodisperse particles. So that's on the x-axis. And then we also determined the number of particles determined by the crystalline software, and that is on the y-axis. So that is n. So this gives a relation between suspension density we put in. We know that in the case of the monodisperse particles, and the number that is measured by the crystalline software. So now we can use this to translate the number we measure during a single seed experiment to a suspension density. So this is what we did. So here you see the suspension density as a function of time after seeding with the single crystal seed for both a seeded experiment and an unseeded experiment. And these two experiments undergo the same procedure, exactly the same procedure, except for in the seeded experiment we add a seed, and in the unseeded experiment we don't add a seed. So in the unseeded experiment, you see the suspension density rises after around 60-70 minutes. And in the seeded experiment, it is much earlier because the seed crystal initiates secondary nucleation. So the rise in this suspension density, so we took a value of around 10, so we took a lower limit value to make sure that we really measure a rise in suspension density. So the rise in suspension density, the slope in the suspension density with time, determines the secondary nucleation rate. So we can count with the software the number of particles as a function of time, and all these particles must have been generated by the presence of this parent crystal. So we can determine the nucleation rate caused by this single crystal by determining the slope of the suspension density in time. So in this case, in this experiment, it turned out that we have a secondary nucleation rate of around 13,000 per milliliter per minute. So we can do secondary nucleation rate measurements at different supersaturations, and what we found there is that the secondary nucleation rate increases with the supersaturation ratio. So the larger the supersaturation ratio, the more fragments are created. And we also found that if we extrapolate towards lower supersaturation ratios, we find a secondary nucleation threshold, which is roughly 1.03 in the case of isonictinamide in ethanol. So this secondary nucleation threshold might be a very valuable information in the design of crystallization processes. Below this value, you don't expect secondary nucleation to happen. So we used this secondary nucleation rate measurement method in the workflow. So that would be in stage 5 of the workflow, where we investigate system understanding. So this stage 5 for the secondary nucleation understanding consists of measuring the metastable zone width and then choosing a supersaturation within the metastable zone so that you can measure induction times at the selected supersaturation ratio. And once you know the induction times and you have a process window to do single crystal seed experiments, you can measure the secondary nucleation rates at the selected supersaturation and possibly determine a secondary nucleation threshold. And this can be used to further design your crystallization process. So that brings me to the end of my lecture on solubility measurement methods, primary nucleation rate measurement methods, and secondary nucleation rate measurement methods. So there are many people to thank, especially Maria Briuglia, who developed the secondary nucleation rate measurement. I made a list of all the literature I produced on these methods the last few years, so I can make that available